055, Mayday, Mayday, Mayday.
Friends, today I will try to explain the lubrication system of gas turbine engines. Lubrication systems are vital systems for gas turbine engines.
Gas turbine engines utilize lubrication systems, similar to those in automobiles, to protect moving parts from wear and to clean them. The lubrication system extends engine life, reduces friction, provides cooling and cleaning, and prevents corrosion. If you're ready, let's take a closer look at the critical functions of engine lubrication systems together.
Functions of the lubrication system. In general, the functions of the lubrication system are as follows. Reduction of friction. Friction is inevitable in regions where mechanical parts interface. Oil prevents direct metal-to-metal contact by forming a film layer between these surfaces. This results in decreased heat generation and reduced energy loss. Prevention of wear. Wear associated with friction reduces component service life. Oil slows down this process, ensuring equipment operates healthily and efficiently for a longer duration. Cooling. Moving parts generate heat during operation. Oil absorbs this heat, carries it away from the system, and prevents overheating of the components. Corrosion prevention. Oil prevents the formation of rust by cutting off the contact of metal surfaces with moisture and air. Cleaning. Oil picks up metal particles and contaminants resulting from friction and transports them to the filters. Thus, the system remains clean over long periods of operation.
Turbine engines incorporate shafts rotating at thousands of RPM, high temperature zones, and numerous bearings and gears. Therefore, lubrication systems must lubricate such complex systems efficiently and effectively.
Protection of main bearings and gears. In gas turbines, the turbine shaft, compressor, and other rotating components operate at extremely high rotational speeds. Friction occurring within the bearings of these components can lead to system failure in a short period. Lubricating oil protects these bearings. Heat transfer. Secondary cooling is critical to prevent damage to metal components caused by the high temperatures generated, particularly in the turbine section. The oil absorbs heat from these regions and transfers it to the oil tanks or heat exchangers. System cleanliness and sealing. The oil flushes microscopic metallic wear particles away from the rotating components. Furthermore, it provides sealing in specific areas to prevent the ingestion of external dust or foreign particles. Venting and pressure equalization. Lubrication systems also incorporate vent lines to balance internal pressures. This prevents the buildup of excessive pressure within the bearing chambers. In conclusion, lubrication not only ensures higher operational efficiency of machinery, but also forms the foundation for safety, longevity, and cost-effectiveness. In systems operating under high speeds and temperatures, such as gas turbine engines, the significance of lubrication increases exponentially. Therefore, proper oil selection, scheduled maintenance, and continuous system monitoring are indispensable for both performance and flight safety.
After explaining the functions of the lubrication system, let's take a look at how it works.
The resource we will use in our lessons will be the CFM56 engine, which is frequently used in civil aviation.
The general CFM56 engine lubrication system is a self-contained, center-vented, and recirculating type system. Each engine features an independent oil system to provide lubrication and cooling for the main engine bearings, radial drive shaft bearings and gears, as well as the gears and bearings within the transfer gearbox and accessory gearbox. The oil system consists of the following: oil storage system, oil distribution system, and oil indicating system.
Now, let us examine the operation of storage, distribution, and indication in the oil system.
Storage. The function of the oil storage system is to retain a sufficient quantity of oil to ensure a continuous supply to the oil distribution circuit. This system allows the operator to check the oil level and replenish the system. Oil is contained within the oil tank. Distribution. The function of the oil distribution system is to provide an uninterrupted supply of oil to all units and consists of three main circuits. These are the supply, scavenge, and vent, breathing circuits. Let's examine the functions of these circuits. Supply circuit. The function of the supply circuit is to deliver oil to the relevant areas to lubricate engine bearings and gears. Oil leaves the tank and reaches the lubrication unit via an anti-leak valve. The lubrication unit pressurizes and filters the oil. The filtered oil is then directed to the engine. Scavenge circuit. The function of the scavenge circuit is to collect used oil from the engine. The oil first passes through the lubrication unit, which also assists in the scavenging process. The oil then flows to the scavenge oil filter and from there to the servo fuel heater. From the servo fuel heater, it passes to the main oil fuel heat exchanger and finally returns to the oil tank. Vent circuit. The vent circuit is responsible for balancing air pressures within the oil system. An external vent line is connected to the oil tank. Any undesirable air pressure generated in the system is discharged from the oil tank through this vent line. Indicating system. The oil quantity indicating system transmits oil system data to the display electronic unit. This data includes scavenge oil filter bypass warning, low oil pressure warning, instantaneous oil pressure, instantaneous oil temperature, and current oil quantity.
So far, we have briefly covered the storage, distribution, and indication systems.
After explaining the functions of the lubrication system, let's take a look at how it works.
Operation of the oil system in CFM56 engines. Oil supply circuit and engine controls. The oil tank stores oil for continuous distribution through the supply system. 4 positive displacement pumps are driven via a single shaft powered by the accessory gearbox. Oil flows from the oil tank through the anti-leak valve to the supply pump within the lubrication unit. The pressurized oil from the pump is filtered through the oil supply filter and then delivered to the main bearings, radial drive shaft, and gearboxes. Overpressure and protection mechanisms. A pressure line originating from the aft sump supply line delivers pressurized oil to the leakage prevention valve, maintaining it in the open position. The lubrication supply pump incorporates a pressure relief valve that diverts oil flow to a scavenge pump during abnormal operating conditions. To prevent structural damage to the system due to overpressure, the pressure relief valve opens when the supply pump discharge pressure exceeds 305 psi. Oil supply filter bypass operation. When the oil supply filter starts to clog, the flow is diverted through a bypass valve. The bypass valve begins to open when the differential pressure across the oil supply filter reaches 17.4 to 20.3 psi. The primary purpose of the bypass valve is to ensure the continuity of oil flow at all costs. The pressure drop represents the difference between the filter inlet pressure and outlet pressure. An increase in this differential pressure indicates the onset of filter clogging. The filter clogging indicators are actuated before the filter reaches a full bypass condition. When the supply filter inlet and outlet differential pressure reaches 11.6 to 14.5 psi, the magnets inside the pop-out indicator repel each other, causing the indicator to actuate and become visible within the sight glass. A bimetallic spring prevents this activation during low operating temperatures. The purpose of the sight glass is to provide a visual indication of filter clogging. Oil scavenge and cooling circuit. After distribution, the oil returns to the lubrication unit from 3 distinct sumps. The forward sump temporarily stores the oil resulting from the lubrication of the number 1, 2, and 3 main bearings. The aft sump stores the oil from the lubrication of the number 4 and 5 main bearings. Oil collected in the transfer gearbox is directed to the accessory gearbox sump via an external tube. Thus, the lubricating oil from both gearboxes is temporarily stored in a single sump. It is then returned by a single scavenge pump within the lubrication unit, passing first through the fuel oil heat exchanger and then back to the oil tank. Scavenge and filtration system. The lubrication unit includes separate scavenge pumps for the forward and aft sumps. Oil collected from the sumps is drawn through the corresponding magnetic chip detectors located within the lubrication unit. The oil is cleared of metallic particles by these magnetic chip detectors. Subsequently, the oil is sent via a single line by the scavenge pumps to the scavenge oil filter. In the event of a filter clog, the oil is diverted through a bypass valve to the fuel oil heat exchanger without being filtered. The bypass valves begin to open when the differential pressure across the scavenge filter reaches 36.3 to 39.2 psi. Oil cooling and heat exchange. Before the oil returns to the engine oil tank, the main oil is cooled within the fuel oil heat exchanger. The oil enters the heat exchanger through the inlet port located on the housing. Oil and fuel flow through their respective channels without making physical contact with each other. At this stage, the heat from the oil is transferred to the fuel via heat exchange. The objective is to cool the oil to ensure it retains its lubricating properties while simultaneously increasing fuel efficiency by preheating the fuel. Leakage drain system. A drain line is incorporated into the forward and aft bearing compartments to capture oil leakage that may bypass the stationary air/oil seals during the lubrication of the number 1, 2, 3, 4, and 5 bearings. The forward seal drain exits through the fan case strut at the 8 o'clock position. The aft seal drain exits through the turbine frame strut at the 6 o'clock position. These oil leakages are considered normal operational losses and are not returned to the oil tank. Oil venting and scavenge system. The bearing sumps and gearboxes are interconnected to allow for the separation of air and oil vapors generated within them. The oil tank vent line, as well as the vent lines from the transfer gearbox and accessory gearbox sumps, are connected to the forward bearing sump. Vapors originating from the oil tank and the forward-aft sumps pass through the rotating air-oil separators located inside the forward bearing sump. The separated air then enters the center vent tube of the main shaft and is exhausted overboard. The reclaimed oil returns to the sumps and is directed back into the scavenge system. In summary, the venting and scavenge circuit collects oil vapors to balance the internal engine pressure. It separates the air from the oil and oil vapor. While the separated air is discharged, the recovered oil is recirculated into the system.
Now, let's examine how the oil is contained within the system through sump seal pressurization and venting.
The engine features 2 sumps, forward and aft. The forward sump is located in the center cavity of the fan case, while the aft sump is situated in the center cavity of the turbine frame. The sumps are designed to contain the oil within the system to minimize oil consumption. To achieve this, these areas are pressurized using labyrinth-type oil seals and carbon seals. These components are utilized to ensure oil retention within the sump by employing circular oil seals and carbon seals that fully encompass the surface of the rotating horizontal shafts. The pressurization air is bled from the engine's primary airflow and injected between 2 labyrinth seals. This air flows through the seal channels, creating a barrier that prevents oil from escaping. Thus, oil leakage is inhibited by air pressure. Any amount of oil that manages to bypass a seal is collected in a cavity between 2 seals and redirected back into the system through scavenge tubes drain lines. Once the pressurizing air enters the oil sump cavity, it becomes vent air and is directed to an air-oil rotating separator. Subsequently, it is exhausted from the engine via the center vent tube, the rear turbine rear frame extension, and the flame arrestor.
Up to this point, we have covered the operation of the oil system and its components. Now, let's examine the functions of each component in greater detail.
CFM56 oil tank. Technical description and servicing. The oil tank is a fundamental component of the lubrication system, also known as the oil reservoir. The primary functions of the oil tank are as follows: to store the engine oil, to separate air from the scavenge oil, to provide a means for oil level verification and system replenishment. Location. When viewed from the rear of the CFM56 engine, the oil tank is positioned on the fan case at the 3 o'clock position. While the engine is installed on the aircraft, oil level checks and filling procedures can be performed through a small access door. This access door is located on the side of the engine fan cowling. For full access to the oil tank and its associated components, the right-hand RH fan cowl can be opened. Physical description. The oil tank is equipped with an oil level sight gauge, a gravity fill port, and a pressure fill port. Oil level sight gauge. Positioned on the forward side of the oil tank, the sight gauge is used for visual inspection of the engine oil quantity. Gravity fill port. Located on the upper right side of the oil tank, this port is used for manual filling. The filler cap features a locking handle. The technician releases the handle to manually fill the tank. Oil scupper and drain. During servicing, any oil spilled from the fill port is collected in a scupper connected to a drain line. This fluid is then discharged overboard via the drain. Pressure fill port. The system also allows for replenishment via the pressure fill port. This port is located on the front of the tank, to the right of the sight gauge, and features 2 connectors. Oil tank servicing and capacity. The oil tank can be replenished manually by a technician or by using a pneumatic oil servicing unit. This unit is equipped with an integrated flow meter, allowing the technician to monitor the exact quantity of oil added to the engine. Drainage and maintenance. A drain plug is located at the bottom of the oil tank to allow for complete drainage of the reservoir. The primary purpose of this plug is to remove contaminated oil and sediment that accumulates at the bottom of the tank during engine oil changes or scheduled maintenance activities. Capacity and limits. The oil tank is considered full when it is replenished with 20.9 liters of oil. Although the absolute maximum capacity of the oil tank is 22.1 liters, it must not be filled beyond the 20.9 liter limit to allow for thermal expansion and proper system operation. The oil level is monitored via the sight gauge to ensure the reservoir is serviced to the required level. Requirements for replenishment. The oil tank may require servicing or a complete oil change under the following conditions. 1. Routine operations, post-flight or between flights as required by consumption limits. 2. Maintenance actions, following the replacement of a lubrication system component or after repairs due to external leakage. 3. Scheduled intervals, during periodic engine oil changes as recommended by the engine manufacturer. 4. Oil analysis, when a laboratory analysis or inspection indicates the presence of contaminated oil. For reasons such as these, oil addition or change is performed by a technician. Oil level verification and servicing procedures. Filling and level indication. During the replenishment process, oil is added until the level reaches the shaded area of the sight gauge. The oil tank is considered full when the oil level is within these shaded boundaries. Critical timing and safety precautions. Verification window. The engine oil level check must be performed within 30 minutes after engine shutdown. If this 30-minute window is exceeded, the oil temperature drops, leading to a change in oil volume, contraction. This results in an inaccurate reading on the sight gauge. Wait period. After engine shutdown, a minimum wait time of 5 minutes is required before opening the oil tank filler cap. This allows the lubrication system pressure to bleed off and excess oil to drain back into the reservoir. Safety warning. Opening the filler cap prematurely may result in injury to the technician due to pressurized hot oil spray. Pressure refilling and personal protective equipment. If the replenishment is performed via the pressure fill port, the pressurized oil overflow connector must be coupled first. It is mandatory to use personal protective equipment during all oil servicing procedures to prevent contact with hazardous fluids. Oil specifications. Only the engine manufacturer's recommended oils must be used during an oil change. Mixing different types or brands of oil is strictly prohibited, as it may cause chemical incompatibility and damage the engine. Oil level monitoring methods. There are 2 primary methods for monitoring the engine oil quantity. Visual inspection, direct observation of the oil level sight gauge on the tank. Remote indication, reading the oil quantity digital display on the upper display unit central display in the cockpit. Anti-leak valve and main oil fuel heat exchanger. Primary purpose of the anti-leak valve. The first objective of the anti-leak valve is to prevent oil leakage from the oil tank into the lubrication system when the engine is not operating. Since the oil tank is positioned higher than other components of the lubrication system on the engine, gravity could cause oil to flow into the system after engine shutdown, resulting in a decrease in the tank's oil level. Therefore, the anti-leak valve also functions as an anti-siphon valve. Secondary purpose. The second objective of the anti-leak valve is to prevent the oil in the reservoir from draining out during the removal or maintenance of any lubrication system component. Location and access. The anti-leak valve is located on the fan case at the 6 o'clock position. It is installed on the oil supply line leading from the oil tank to the lubrication unit. To access the anti-leak valve, the fan cowlings must be opened. Functional description. The anti-leak valve is a pressure-actuated valve. Engine static. When the engine is not running, an internal spring holds the valve in the closed position. Engine operating. Once the engine is started, oil pressure from the aft sump supply line overcomes the spring tension to keep the valve open, allowing oil to reach the lubrication unit. Training information point. Caution. The oil tank must be completely drained before replacing the anti-leak valve. Main oil fuel heat exchanger. The main oil fuel heat exchanger utilizes fuel supplied from a low-pressure fuel pump to reduce the temperature of the scavenge oil. The heat exchanger is mounted directly onto the fuel pump assembly. It is located on the fan case at the 8 o'clock position. Functional description. The heat exchanger core is the component where the heat exchange occurs. As the oil transfers its heat to the fuel, the oil temperature decreases. The main oil-fuel heat exchanger is equipped with an internal oil bypass valve. This bypass valve opens automatically if the heat exchanger core becomes clogged or restricted. This ensures that oil flow continues through the system by bypassing the core, preventing a total loss of lubrication. Lubrication unit and chip monitoring system. Components and location. The lubrication unit is located on the accessory gearbox at the lower left side of the fan case. The unit incorporates the following internal components. 4 positive displacement pumps. These consist of 3 scavenge pumps and 1 supply pump. Oil supply filtration includes a cleanable oil supply filter element, a check valve to monitor the differential pressure, and a bypass valve equipped with a clogging indicator. Pressure relief valve, situated on the discharge side of the oil supply pump. Magnetic chip detectors. 3 magnetic chip detectors are positioned at the inlet of the scavenge pumps. They are designed to capture metallic particles before they enter the lubrication unit. Each detector features a removable magnetic plug and a scavenge screen. Wear debris monitoring system. The lubrication unit monitors wear debris through a specialized system. The chip detectors detect free-floating magnetic particles within the scavenge lines and transmit a signal to the display management computer via 3 dedicated wires. Signal path. From the DMC, a single cable transmits the signal to channel B of the electronic engine control. Monitoring. The signal is then interrogated through the control display unit. Maintenance alert. In case of abnormal findings, a DMC message indicating check may be displayed. This message signifies that magnetic metallic particles exceeding acceptable limits have been detected within the engine lubrication system. Electrical chip detectors. The system consists of 3 electrical chip detectors organized into 3 lines. 1 for the forward sump, 1 for the aft sump, and a combined line for the accessory gearbox and transfer gearbox. Design. Each electrical chip detector consists of 2 magnetic receivers mounted on a probe. Installation. The detectors utilize a spring-loaded bayonet lock that fits into a corresponding housing. Safety feature. An internal check valve within the housing prevents oil loss when the chip detectors are removed for inspection. Operation. Return oil from the scavenge pumps flows directly over the magnets positioned at the center of the detector. Debris monitoring system operational logic. The operational principle of the debris monitoring system can be explained as follows. Pure engine oil is non-conductive, meaning it has a very high electrical resistance. However, when metallic particles contaminate the oil, these particles create a conductive path for electricity. Ferrous particles are attracted by the 2 magnetic receivers, causing the measured resistance values to become significant for system evaluation. Resistance value interpretations. The DMS interprets the resistance values as follows. 39 ohms to 130 ohms maintenance alert. If the resistance value is between 39 and 130 ohms, a maintenance required message is transmitted from the DMS to the control display unit. This indicates that metallic debris is beginning to accumulate, potentially signaling a clogged condition. Below 39 ohms or above 4000 ohm system fault. Values in these ranges indicate an electrical system failure, such as a short circuit, an open circuit, broken wire, or a missing sensor. 130 ohms to 4000 ohms normal operation. Resistance values within this range indicate that no significant ferrous particles have been detected by the DMS. Diagnostics and troubleshooting. The system serves as a critical reference for both pilots and technicians for fault isolation and diagnosis. Upon receiving a maintenance required message, the pilot or technician can access the relevant pages on the flight management system display in the cockpit to identify the specific source of the debris, whether it originates from a specific sump or a gearbox. Magnetic chip detector and scavenge oil filter contamination limits. The contamination levels on the magnetic chip detector are classified as follows. Acceptable contamination. As shown in the illustration, this consists of very short particles with a low density on the magnetic receiver or screen. This is a normal condition resulting from operational wear. Unacceptable contamination. This includes large fragments, pieces identified as bearing flakes, flattened particles, bearing race fragments, tab washer pieces, high-density particle accumulation, or long metallic slivers. Warning: do not use an external magnet to clean the particles from the magnetic plug. The use of an external magnet may degrade the magnetic performance and sensitivity of the plug. Scavenge oil filter. The scavenge oil filter is installed between the scavenge pump discharge and the main oil-fuel heat exchanger. It is located on the aft face of the accessory gearbox at the 7 o'clock position. Components. The unit consists of a replaceable filter cartridge and a bypass valve that is designed to open at approximately 38 psi. Differential pressure switch. The oil filter utilizes a differential pressure switch, which is a snap-action, pressure-sensitive switch. Function. The pressure switch is strictly a sensing and warning component. It does not allow oil to flow through its internal body. Connections. The high-pressure side of the switch is connected to the inlet of the filter housing, while the low-pressure side is connected to the filter outlet tube. Indication logic. As the scavenge filter becomes restricted, the differential pressure across the switch increases. When this pressure differential reaches 25 to 27 psi, the switch closes to complete the warning light circuit, triggering the oil filter bypass warning message. Oil indication system and components. 1. Oil pressure transmitter. The oil pressure transmitter is a primary component of the oil pressure indication system. It facilitates the display of engine oil pressure data on the display units. The transmitter sends pressure data to the electronic display units via the electronic engine control. Location. It is mounted on the temperature and pressure TP sensor support assembly at the 10 o'clock position on the left side of the fan case. 2. Oil temperature sensor. The oil temperature sensor measures and displays engine oil temperature data. The system utilizes a sensor located at the discharge of the lubrication unit to measure the temperature. This data is transmitted to the electronic display units via the electronic engine control. Location. The oil temperature sensor is co-located with the oil pressure transmitter on the TP sensor assembly at the 10 o'clock position on the left side of the fan case. 3. Oil filter bypass switch. The oil filter bypass warning system monitors the condition of the scavenge oil filter and displays status data on the common display system unit. The system utilizes a differential pressure switch. This switch is calibrated to close just before the oil filter bypass valve opens. The bypass status is sent to the electronic display units via the electronic engine control. Location. The oil filter bypass switch is located on the scavenge oil filter assembly at the 8 o'clock position on the left side of the fan case. 4. Oil quantity transmitter. The oil quantity indication system displays engine oil quantity data, typically on the upper display unit of the P2 panel in the cockpit. The system uses an oil quantity transmitter to measure the fluid level within the oil tank. Note, unlike other sensors, the oil quantity transmitter sends data directly to the display electronic units. This data does not pass through the electronic engine control. Location. The oil quantity transmitter is installed on the oil tank, located on the right side of the fan case at the 2 o'clock position. Oil indication systems and operating limits. 1. Oil pressure indication. The oil pressure transmitter measures the differential pressure between the oil supply line and the transfer gearbox cavity. It sends an electrical signal to the electronic engine control, which converts it into an ARINC 429 signal, a standard digital communication protocol that allows the engine control unit and cockpit displays to communicate. Display format. Oil pressure is typically displayed on the secondary engine display. It features 2 vertical analog scales and 2 digital readouts. Pressure is indicated in differential PSI. Limit indicators. Amber index mark indicates the cautionary oil pressure limit. Red index mark indicates the maximum minimum operational limit. Color logic. If the pressure is between the amber and red limits, the digital value and its bounding box turn amber. If the pressure falls below the red limit, they turn red. Dynamic limits. The low oil pressure amber limit is dynamic. It increases as engine speed, RPM, increases. 2. Low oil pressure alerting logic. When oil pressure drops below the red limit, the EEC triggers a low oil press message on the primary engine display. Annunciation. The amber message flashes for 10 seconds before becoming steady. Inhibits. To prevent pilot distraction, the flashing mode is inhibited during takeoff and landing. Furthermore, during engine start, the EEC inhibits amber-red indications and oral warnings to prevent nuisance alerts while the pressure is naturally low. 3. Oil temperature indication. The oil temperature sensor measures the oil temperature in the supply line to the forward sump and transfer gearbox. Like the pressure data, This is converted to a rank 429 by the EEC and sent to the secondary engine display. Display, temperature is shown in degrees Celsius. On vertical and digital indicators. Color logic, similar to pressure, the display turns amber between the amber and red indexes, and red when exceeding the maximum limit. 4. Oil quantity system. The oil quantity indication system displays the reservoir level on the secondary engine display. Transmitter logic. The oil quantity transmitter is a resistive sensor using a floating magnet and magnetic reed switches. As the magnet moves with the oil level, it opens or closes different resistance circuits. Data path. This transmitter sends data directly to the display electronic units. It does not pass through the EEC. The DEUs provide a low excitation voltage and calculate the quantity based on the return signal. Units and range. Quantity is displayed in US quarts. Full capacity, 21 quarts. In other words, 20.1 liters. Measurement range, 2 to 23 quarts. 5. Low oil quantity and reverse video. A low oil quantity alert occurs when the level drops below 4 quarts, in other words, 3.8 liters. Reverse video. The quantity value is displayed in reverse video. In cockpit displays, where text is usually light-colored on a dark background, reverse video swaps this dark text on a bright or white and amber rectangular background. This acts like a digital highlighter to ensure the pilot immediately notices the critical value among other data.
Yes, friends, we have come to the end of our topic about gas turbine engine oil system. To see you in new videos.